Hi, Lee, Linda. This is Richard Collins, and thank you for the nice note and the attachment. I'm looking at that. In fact, let me mention that first. I've been working quite a bit lately, and I'm rather tired, so I I can't. I don't know if this cursor is going to show up on there or not. On the frame rate in frames per second is what I'd like to get. Um, Frame rates like 100,000. Actually, I'd like to get up to a billion frames a second for some things that I'm looking at. But even 100,000 frames a second. And here, what I think of these as independent measurements or samples, like statistical samples. So I'm gathering some data, and it's sending me the results of the measurements at that many times a second. So a million samples per second is more what I'm thinking of, or a million measurements per second, that kind of thing. Let me go through here and give you an idea of where I'm at right now. I'm not interested in the light falling on the sensor at the moment. I'm literally excluding that. In the note, I'll say I don't care about the camera body. I don't care about software intended for users of cameras. I don't have any particular interest in, I don't need to know about the lenses. I don't need to know about lens mounts, anything of that. So I'm starting at the raw sensor. And even more than that, what I'm doing is looking at specifically at the electrons at the pixel locations themselves. There's a well of electrons there. Basically, it's a capacitor storing a finite number or no electrons, and it's sort of filled in. There's all kinds of fields at that location from the matrix that the electrons are in, and then there's in the optical sensors there and many other sensors, there's an amplifier there to detect any electron, to accelerate the electrons coming out and then send them into an ADC. So there, let me step back a little bit. I started this looking at gravitational signals about 15 years ago, actually much earlier than that, but in terms of actually measurements and using instruments to process signals, I started with the superconducting gravimeter network, and I wanted to do a speed of gravity experiment. So I started, because it was available on the web. I don't have any access to instruments myself, but I do have access to some data if I'm willing to learn how to use it and clean it up and understand it, try to dig deeper and figure out what in the world the instruments are doing, and then do something with it. That's a long story. I'm not going to get off on that end of there. But the superconducting gravimeter measures the gradient of the gravitational potential. It is an acceleration signal. And unfortunately, I did do the speed of gravity measurement. It came out identical or very, very, very close to the speed of light, and later other people did that, so it's no big deal. But it wasn't a 3-axis machine, and so the results were ambiguous. I couldn't precisely or unambiguously localize the sun and the moon with the network. Okay, I could assume that the local vertical matched the direction of, the absolute direction of the signal, but I couldn't be sure about the scale of it because I didn't have all three axes. Anyway, from there I went to the seismometer network, so earthquakes. I spent several years looking at that. Over a period of about 6 months, I went through all the data, decades of data, looking for all the sensors, the seismometers, used as accelerometers, which were sensitive enough to see the sun and moon signal. Okay, the sun and moon signal is the primary, about 95% of the gravitational signal at a superconducting gravimeter station. So I looked at the earthquake data. Now the signal is quite complex. Over the years, it's been more than a decade I've been looking at this now. What I've found is that there's many interwoven signals. There are weather signals because the ground shakes and the wind blows and the building shakes and the pressure changes and the sound changes. The electron density changes, all when there's an atmospheric storm. Ocean waves nearby, ocean currents, rivers, rainfall, rain falling onto the ground, cars driving by, lightning, temperature variations in the equipment, all kinds of things affect the signal. So I've learned to separate all those out. And these are roughly the kinds of things that get into every signal for every instrument, every analog instrument on the planet. And as such, they get into the digital signals as well. So I've been trying to sort these all out. There are quite a number of, I have about 40 different sensor networks that I'm looking at, types of sensor networks, and there are millions of sensors around the world now of this type. So let me see if I can get. So people affect the signals. Now, I have here magnetic, electric, electromagnetic, and gravitational. Those are the main themes for the kinds of things that are coming in that an electron will see. Because it has mass, it's affected by the gravitational signals. Because it has charge, it's affected by the electric field and by changing magnetic fields. And I separate these out because basically magnetic means very low frequencies. Electric means very low frequencies. And electromagnetic is more, the kinds of things that people talk about when they're talking about, varying signals. So those go anywhere from 1 hertz up to whatever, zeta, is it zeta now? I can't, anyway, I know all of them. I just can't keep them all in mind at once. I have to put them in a list and organize them in databases. I can't. My memory's getting bad now. It's hard for me to keep track of them all. So anyway, so I'm looking at this fundamental thing, and so I'm also going out and looking at the semiconductor designers, the people who are doing this. On the gravitational signals, I'm tracking all of the MEMS gravimeters, the electrochemical, Bose-Einstein, atom interferometer gravimeters. I've looked at LIGO and all the gravitational potential sensors. Okay, if you have a gravitational potential and you take its gradient, you get an acceleration. The gravimeters measure the acceleration. So there are instruments like time dilation, GPS time correction sensors that look at the change in the rate of clocks because the gravitational potential changes, or because the velocity changes, or because the magnetic field and electric field change. So there's a whole bunch of stuff going on there. So there are direct gravitational potential sensors, and then there are the gradient ones. And I'm looking here at primarily at the gravimeter, the gradient gravitational signals. Okay, what they are, that means an acceleration for an electron at the thing. These are tiny. Okay, and you have to remove all the other data. But if you have a lot of data, okay, then you can play some statistical games and tease out the stuff. The seismometers, when I was looking at the earthquakes, the seismometers have, they look like pure noise. It took me 3 months about working, I generally work 12 to 18 hours a day, 7 days a week, so quite a bit of time that I took to just keep going on faith, looking inside there to see. Now there are some big signals in some of the quiet stations. Sorry about the noise in the background. Oh, yeah. So, but in terms of actually matching it to the sun-moon signal, to a reference signal that I had, it took a long time, and it was extremely noisy, and I didn't know what the instrument response was, and I didn't know all their terminology, so that was kind of a tedious process, but it was in there, and I learned what makes a better sensor for that, using to use the seismometer as a 3-axis gravimeter. Sorry. Okay. Now for this, okay, I think there might be enough. There's definitely enough information in the electron statistics based on the voltage and gain, the reference voltage and gain in the electron well, or the whole well in some cases. They also call them quantum wells and those things, to pick up lightning. So if you have a lightning stroke, it should show up in the pixels. Now, if you were looking at light from the sensors, if you were using it as a camera, all bets are off. You probably won't see much at all because it's being swamped. But if you cover it and block out the light from the sensor and look strictly at the dark current, then you have a chance to do it. Now, let's see if I can draw this. Hang on a second. Okay. So what? It's been a while here. Okay. Pencil. Okay. Well, I'm doing black. Okay, so they usually draw it like this. Okay, here's all. I can't even draw that many. Okay, so you have electrons in a well. I'm sorry, this is not really, should be done in 3D. Okay, and some of them hop out and eventually get to the ADC. Goes through the amplifier and go to the ADC and show up as a signal, a delta in the amplitude. Sorry, for the signals. I wish I had a better thing to draw with. Okay, so if the gravitational field changes slowly over a period of time, and sort of, if you want, I'm just using very loose words here, it leans in this direction, it would increase the frequency of those. And if you have an array of these pixels and you draw from a pixel over here and a pixel over there, or if you have a whole sensor here and one here, then you can gradually piece out what's happening to the specific electrons. This game is being played all over the world right now in so many different areas. They generally tend to think like, okay, here's my B field, and it's a function of time. Or here, this is like an acceleration field as a function of time. And we can look at statistics of various sorts and begin to get a sense of what's going on here. Okay, well, I'm sorry that's so crude. Okay. Um, so that's what I'm trying to do. I'm trying to look at signals. Most people just call it noise. Okay, I got power system noise that's getting into my sensor. I've got thermal noise. I don't even have that local noise in the sensor. I say, oh well, the lattice is shaking and it's causing the electrons to slosh around and they're jumping out at random, and I got that kind of noise. Or I've got nonlinearities in my system, and it's generating other kinds of noise. I'll deal with that later, or I'm dealing with it. I just don't want to talk about it at the moment. Okay, so all right, here. Okay, I have a Windows Intel i7. I think it's got 16 gigabytes. It's a good solid machine I've had for many years, and I've pushed a lot of data through it. When I did the gravimeter network, which was decades of data for about 25 instruments spread around the world, I was doing that on an old laptop, like a little better, it was better, not quite as good as that. And when I did the, it was, and the same thing when I was going through decades of data for, I think there's close to 5,000 instruments in the seismometer network. So I went through literally all of those. And lately I've been going through and downloading all of the seismometer data for earthquakes from every channel, from every instrument. And those are in the range of 5,000 time series at 40 samples a second. Anyway, sorry. Okay. So I just got an NVIDIA Jetson Nano, and it's sitting here. I'm not even playing with it too much. They're playing games with their the way they set up their the system and where they're getting their software and how it's arranged and how they relate to you. It's a big mess, I think. Anyway, roughly the same. I feel the same thing about the Raspberry Pi. There are a lot of people. I'm looking at many global networks that are based on Raspberry Pi. It's a good local processor, but they're not writing in assembler. They're not compiling down to native code in many cases, and they're very inefficient. So they're only getting a fraction of what you could out of that processor. And I'm interested in the algorithms primarily, and these are hard questions at the scale of trying to tease out gravity there. Okay, I've got a Windows 10 machine, several Arduinos, several Androids, and I've been buying these things like Cracker Jack boxes whenever I need them. Because I've been the Internet Foundation for the last 20 years, I look at my final audience is the whole world, everybody on the planet using information and knowledge and sharing on the Internet. So I tend to stick with JavaScript, and for various reasons I've been using Chrome for my browser and using their extension. So I have a lot of JavaScript tools that I write, and I run with a local IIS host. I send my instructions from a content script on Chrome to the IIS host and ask it to read files, write files, give me a list of directories, give me a list of files, read all the files on a disk, read all the data from a thing, and so on. I did the same thing with Node.js. My son, encouraged me to try it, and I basically everything that I'm doing now with IIS, I also did with Node.js. So that was a couple of years of experimenting. But a lot of the instruments and like the USB and cameras and sensors, I can only get to at a reasonable speed by going through Visual Studio using VB.net or C.net. in something. I used VB. I'm old enough. I'm way older than the IBM PC, and I had my first personal IBM computer in 1967, 66 or 67, because the local university let me use their computer. I was already designing computers in high school, and they sort of rewarded me by letting me use this computer for myself. So anyway, this thing here, okay. I've got a pixel over here. It's got electrons in it. I want to know what's happening to it. If I could get something that would say, send me the data from that pixel at 10 megasamples per second. I presume the ADC gives me, say, 2 bytes of information, 12 bits, 16 bits, whatever it's able to do. I'd like to say, for that one pixel, give me the maximum stream, or give me 2 pixels, wherever. Now, I don't have quite the ability to go in and build like take a chip and put like 5 or 10 or 100 processors on it and say, here, you watch this region, you watch that region, and what I'm doing, and then correlate all of them and use that. I have the statistical and computer processing ability to take that after the fact, process it, and get real information about the world from it. What I can't do is get it where I develop like an algorithm that reduces and gives me statistics relevant to the real world that I can put on a processor next to the chip to read a specific region or sample of regions and only give me statistical summaries. Let me go back here. See, the raw stuff is too big to send back to most things. The bandwidth for USB 3 isn't enough for many of the things I might want to look at. But I could, for almost anything, if I can get a local processor, I first run and get raw data. I take that offline and spend weeks or months figuring out what the core of the thing is. Actually, now I've got it down because I've gone through so many different kinds of data streams. I have a standard way to process pretty much everything. Any time series or any set of time series, I can process it, get down to the essentials, get that information back to a local processor, and then have it send statistical summaries. Now, I haven't done. I have another project going where I'm looking at the light falling on optical sensors, and actually light falling on single sensors for single pixel camera type things. So a whole bunch of stuff going on there. But for what I'm doing here, trying to learn about the electrons in the wells for each pixel in an optical sensor, I'm narrowing it down to this. Let's see, how long is this? Try not work. I'm going to pause for a moment. I need to get something to drink and take a break for a moment. I'm going to pause. Okay. Thanks for the break. This is a spreadsheet that I built. I tried to look at, I first came to this idea of using the optical sensors, basically semiconductor devices in massive arrays as sensors, thinking of rows by rows. I've been, getting 30 frames a second, up to 1,000 frames a second if I spend some money. I've done a lot with, 60 frames a second, statistics and experiments. Then I got to thinking, that the row by row sensors, that they read them row by row. The first row of the sensor has is taken at one time and the next row at a different time, and basically the time series of of the rows for a sensor where every pixel is being affected by gravity or electric fields or magnetic fields or electromagnetic fields or acoustic waves or seismic waves or whatever might come to that set of electrons, those are samples of the electromagnetic environment, the gravitational environment, at so many rows per second. So I was playing things like trying to find ones where they were called rolling shutter, assuming that somehow or other, I haven't even done this yet, assuming somehow or other I can pull out each row of the sample, each row of the data that comes to me, and assign each pixel a time. Since the rows are locked at once and read out, I pretty much have to take them row by row. So I was just looking at that for some things and just going through some numbers. So I have some different cameras that I've acquired. I have like 20 or 30 little cheap USB cameras that I've looked at, and I do it because I'll run them for a day and look at the statistics, and all of these are dark field. I do a few things where I have them look at scenes, but I'm just looking at the covered sensor, and is dark noise. So here, this is 89 billion rows a day. So that's a decent improvement. And then I was looking at the pixel improvement. How many bits does that add to precision? That sort of thing. Let me move this off. Let's see. Now, then I found that the area of interest, like if you have a 5 by 5 pixel area, and you have a maximum, anyway, so I tried that, and then I learned about, what are the limitations. Everybody had limitations, we're getting up to USB 3, but then they actually only do 60 or 100 megabytes per second, so a lot of advertising to get through. Anyway, so even relatively small samples, where I could read individual pixels or regions. I mean, I don't have any problem if I have some way to specify what the statistics are, or if I have a 10 by 10 region or something like this one, I guess is 5 by 5. Let me see if I 10. I did that change here. Sample size in pixels. Oh, I see. This is a. Let me just change this so I use those up there. Oh, I missed it. Sorry. Okay. So now if I can do a 20 by there. Okay. So that changes. Now, what's going on here? I take these nominal. Actually, I take these, and then this is just created. So I have a 30 frame per second, 640 by 480 sensor, and it's giving me this many pixels per second, and this is 2 bytes per pixel. This was an example. Let me see if I can. What I want to do here. That's just for the byte thing, but the samples per second, in this case, a 20 by 10, let's go back to 10 by 10, make it easy. A 10 by 10 area, that's 92,000 samples per second, if you could read it that much. Now, at the speed of light, or the speed of gravity, that many samples per second means a 3 kilometer spatial resolution, a little over 3 kilometers. So if you're looking at, say if you have an array of these kinds of sensors out there, and they're looking at something, 1,000 kilometers away, if your resolution is 3 kilometers, then you can kind of localize it. For an earthquake, that gets you in the ballpark of the world, and then you can call in other sensors to go look. So I'm looking at global sensor arrays that are very, very sensitive by whatever means, and then they can pick up the gravity signal from an earthquake, anywhere on the globe. Maybe, but then you call in the other arrays to do fine scale resolution, and if somebody's got a really you don't really need a supercomputer for it. Actually, I can do it on a laptop, but you can monitor the seismic waves as they go out. So you have a model for the seismic waves, the displacement of the change in density that the earthquake generates in the earth and the sky and the oceans as that energy goes out, and then you look at the gravity from it and you calculate how that looks at the stations. So anyway, these rows per second are there. Now, let's see, I'm not quite, in an oscilloscope at a gigasample per second, you're basically getting a measurement. So instead of rows per second, you can think of this as measurements per second. So that's roughly the game I've been playing there. I don't know, this ASI 224 is a USB 3 color thing. Sony is the only one I've sort of found some specifics on where it says, yes, we can do pixel sampling. So that's there. And some of the cameras are surprising. The action cameras have pretty good stuff, but that you can't get any data out of them. So you basically need to go get one of those chips, put your processor right next to it, speak bits and bytes to it, at a hardware level, and then process it. Now, from any one of those sensors, they could be remote once I've processed the raw data enough to know what are the specifics you want to look for. I wish I could see. Let's see if I can explain this. Let me pause for a moment again. Oh, good. We're going again. All right. This is some seismic data. It's from what's called an STS, Streckhausen 3-axis magnetometer, which is sensitive enough to over long periods to track the sun and the moon, at least at some stations. Every single instrument, every single channel of thousands of instruments and many more channels is unique. And what I've learned to do is to look at the data series that is coming out of there and break it up into specific signal sources. So this is an acceleration signal in there. These are all, I think I've done, these are deltas. So these are, they report velocity, you differentiate it or difference it, and you get an acceleration signal. Anyway, so you have this fuzz down here, which actually has a lot of information about the local instrument itself. And what I do is I basically triage. I go in and I say, look, select these regions to send to the seismic processor. Okay, these get, these are quote seismic, meaning send them on to a processor that specializes in interpreting seismic data, correlating that, and then down in here you'll have at least for this instrument anyhow, down in the noise, the gravity signals and the long-term gravity signals from the sun and the moon, or possibly that I was trying to pick up and see if I could use the whole array of seismometers as gravimeters, and see if I can pick out the early signals, the gravity signals that are coming directly at the speed of light from the earthquake and its outgoing seismic waves to the censored, the seismometers anywhere. And those are all that. We also have the superconducting gravimeters that can pick it up. And I'm waiting. There are a couple of MEMS gravimeters that are one in China, one in Scotland that they're designing, and they said they might be ready in the next year or so. So we'll see. Anyway, but this is the kind of data I work with a lot, and you would think, oh well, I can't get much out of it, but there are some fairly simple things that I found. For instance, almost all of the, almost all the deltas are going to look like this. They're all going to be normally distributed. And one way to simplify it is to say, look, just collect all the noise down there that this stuff, right next to the zero in the thing, and treat it as a separate signal. And then that you can say, well, look, we can just represent it with a normal curve in here, basically, and then look at the differences from that and begin to chop it down level by level and all. And then, okay, so when you do this and put it back onto the original time series, you get exceptions again. And so you play the game one more time. You say, look, these are the spikes on the delta. Treat those and look at them. These are the, these are the second differences, the third differences. So basically, I'm taking if in math physics terms, it's a Taylor series. The coefficients for the time derivatives, the first, the velocity, the acceleration, jerk. They're actually called snap, crackle, and pop past that. So, excuse me. So, let me get this out of the way. Okay, so I wish I had some there's some absolutely gorgeous fits sometimes. For some sensors, the delta curves fit exactly on what you're getting, and so the noise, basically the compression on that is about 98%, because everything, all of that part of the signal is pretty much exactly matched. And if you run this, say you have a sensor that you're running for a decade, even at 1 sample a second, that is, let's see, 86,400 seconds a day times 365 days a year times 10. 1, 2, 3, 4, 315 million data points to narrow down, looking at the noise in there, just to characterize the instrument response and all. So I do a lot of stuff where I take the first differences and then I count them. I take the incoming amplitudes, count them. I take the pairs. So, one signal, at one time, and then the next one, and then I count the transition. So if it goes from, let's say this was a data stream, and I would say, oh, okay, I got a 30 followed by a 30. Now I have a 30 followed by a 30. So I would, so basically, however large the space is, if I've got I'll provide enough memory, or just keep track of which ones occur uniquely, and then I'll count all the transitions. And I've gone up and investigated for some signals, fourth and actually up to about 10th transitions. I did one where I looked at the 10th time derivatives of things, and I looked at the statistics in detail. This is a variation on what's called Bayesian statistics, conditional probabilities. So what is the probability of a 30 given that I'm sitting at 30? What's the probability of a 60 coming next if I'm sitting on a 30? What's the probability of a 5 coming next? And you can get that and cover the entire space if you have enough data. So you have to, basically the game is get enough data to fully qualify and characterize the space of possibilities, and then work from there. And then you can flip it around right away and use it for simulation. So you can basically say, like, given this set of statistics, what's run me a simulation and see how this is, whether I can pull data out of a new sensor that I've designed or something like that. All right, well, I apologize for these. I'm trying to summarize quite a bit of stuff I've been looking into. On these sensors, I'm just frustrated right now because okay, let me get this out of the way. I am, I'm getting old, and I work on Windows Intel 7, and you can see I do a lot with Excel. I can write fluently in JavaScript. I'm pretty good at C. I just hate their library management and all. VB I've used for 20 years. I'm going back to it with VB.net because I don't have any choice for getting to there. I've looked at all these expensive packages and things, but it just wears me down to think about having to go and relearn, everything that's in there. Learn their way of doing it. I've been through whole generations of people, reinventing new things that were old when I was young. So I don't know what to. Let's see. How can I say that? So, if I could get a device, just if I could get a sensor, okay, that I could talk to from Windows directly, like can I stick a? I've looked. There are such things. I just don't know how to get all the pieces together. Where I would have a program running on Windows that would go through, say, an Ethernet to a sensor. Now, it's cheap to buy an Ethernet 10 megabit per second adapter. USB 3 is pretty good. And that's what I've been doing. But USB underneath is kind of ugly. I mean, it has a lot of layers. I found it confusing. I don't have a good set of drivers. I don't have a way in Windows to go in and like speak to every sensor. Even these cameras, all the ones that say, well, here, use this app and control the sensor and all. They have no clue about statistics. They don't care about it. They're just trying to pump out this MP4, whatever the latest video data stream is for people to look at. I don't want to look at it. I want to calculate things. I want to collect the data, run it through models, compare it globally to what other people are getting. I want to do science with the sensors. So anyway, that's about there. NVIDIA is really biased. You ought to see this thing. It's got this massive, video processor thing he's sitting on there, and they didn't do a very good job of, doing the software and the software development. What are you trying to use this for? Well, they don't know. They just have this wonderful NVIDIA, graphics thing that they want to sell, and they stuck it on top of this other thing. So anyway, I don't know, all these people. So that's roughly where I'm at right now. if I weren't so tired, maybe I'd be a little more elegant at this today. But that's it. So I'd really like to get the, I'd like to track the sun and the moon with a global network of sensors. I've been at that for roughly 15 years. I've helped people identify what you need to have a sensor that'll do that. And this idea of using, basically, of all the different methods of measuring gravity, I'm talking about gravimeters here. I know how to get down and do the direct gravitational potential sensors. There's a lot of very wonderful ways of doing that, but for everyday practical stuff, the gravimeters are probably more useful on the Earth, and for things like imaging a car driving by, or tracking people, or even every frequency that is accessible to electromagnetism is also accessible to gravity. You just have to push the numbers and build it sensitive enough and do it. So basically, it's now down to, I call it gravitational engineering. You just say what you want to do, and then you just keep putting the pieces together until you get it done. So let's see what we can say. Okay. So my point was, they used heavy masses in, like grams or kilogram masses in the seismometers and accelerometers, and they watched the mass move around, and they took the second derivative of the lengths involved, and they got accelerations. They say, we're measuring gravity. Gravity and acceleration are the same thing. We have a gravimeter. Okay. When it could track the sun and the moon, which is so elegant. I wish I could stop and show you what the signal looks like, but it's like a perfect fit, and all it requires is a linear regression of GMM over R squared from the sun minus GMM over R squared for the from the sun to the station minus the sun to the center of the Earth, from the moon to the station minus the moon to the center of the Earth. That's a vector, a vector expression. It's a vector, and acceleration. And then you add the local centrifugal acceleration at the station. You take that, dot it into the local north, east, and vertical unit vectors, and it exactly matches all three axes of a three-axis gravimeter with a linear regression. It's that close. Now, are there some funny things going on there? The X, Y, and Z axes of a seismometer are generally not calibrated exactly, but with the linear regressions to the sun and the moon, bang, it's you can basically continuously calibrate it and take off all the drift. It's an elegant technique. All right, well, let's see what else. I don't know how to get to get to the point. I can write these kinds of programs. I can do them in my sleep. I have probably tens of thousands of programs like this I've written in my life, and my disk is full of examples where I've taken sample after sample, non-real time, worked out methods that work really well, and I just want to apply them to real-time data, or have the sensors know what kind of data to collect so that you can offline use it. So the ionospheric people use GPS because the GPS signal noise relates to the electron density in the ionosphere. Lightning modifies the global electron distribution. Earthquakes affect the electron distribution. Ocean currents do. storms do, power systems do. So if you look at every electron on the surface of the Earth, in the atmosphere and inside the Earth, if you look at basically the whole Earth and only the electrons, then all these different things are affecting them. And so even the pixels inside, 30,000 electrons or 1,000,000 electrons or 5 electrons or 1 electron in a cell, it's being affected by magnetic, electric, electromagnetic, gravitational, acoustic, infrasound, all across all the frequencies. And if you go through bit by bit and look closely at the signals, you can pull all that apart. I'm repeating myself. I'm going to stop here. I ask questions. That's all I know what to do. I'm going to try to force myself to learn, to learn these things. Let's see. This Sony thing, I have gone through some Sony ones that I could read, and my problem was I came in here and it's just getting harder for me to read. Okay, I don't know, I got to go through and find out what is the coarse integration time. The frame length in lines, does that mean a region of interest frame, or does that mean the whole frame? Pixel clock frequency in megahertz, well, I don't know exactly where to find that. So even though it looks simple, by the time I go and say, well, what should I use for the time for line? If I guess wrong, I could spend a lot of time going in the wrong direction, just simply having the wrong numbers in here. Now I can make a spreadsheet, and that's what I'm going to do. I'll make a spreadsheet for this particular thing, and then I'll go in there and try to figure out, read this thing and see if they give me any clues. They don't give a single calculation in here of one, or at least I have to go through and try it. But if you say, here are the equations to apply, I mean literally, and what are, show me the numbers, and so I know exactly what to stick in here. This stands in the way of anybody using any of these devices. The manufacturers don't, or whoever writes these things, are so familiar with it. They say, oh, I can find that instantly, or I already know that, and they don't put it down. And they don't even put down enough clues to find it. Say like, oh, it's like somebody, I do a lot of genealogy, so somebody says, oh, I'm related to John. Well, how many Johns on the planet are there? Or I'm, anyway, that, so I will try to go through this and see if I can, so frame length equals coarse integration time per line. Because it's dividing the time per line, it makes me think that they're only doing row by row. And the frame length times the frame, so, and they're, are they, I don't know. And again, I don't care about frames. What I want is measurements per second. So if they had 16 regions that were sampled simultaneously, and they all came out for every clock tick, so I could get a pixel per clock tick, whatever this maybe that's what this is, the pixel clock frequency in megahertz. That's encouraging. So if I could get, 1 pixel per pixel clock frequency, whatever the clock frequency click, then I could get presumably mega samples per second. And get good spatial resolution. So that's the whole purpose of this in here, is to get sufficient spatial resolution, time resolution, to use time of flight methods to locate things like, oh, I've got an ionospheric disturbance. It sends a magnetic signal down to the sensors. I got a whole array of these around the Earth, and they can each measure when that particular signal arrived at their location. Or I've got an earthquake occurring over here, and that earthquake is sending, direct gravity signals over. And so when did they arrive? Well, it's just a numbers game. If you have enough information coming in, you can do the correlations and you can do those kinds of calculations. It's not complicated. It's what I call not hard, just tedious. You know, it's engineering. You know what you need to get. You go in and keep working until you get it. So anyway.